Have you ever actually stopped to think about the invisible language powering, well, absolutely everything around you? From the screen you're looking at right now to the lights overhead, our whole modern world relies entirely on this silent, continuous conversation of energy. But if you've ever tried to crack open an electrical engineering textbook, yeah, that beautiful conversation usually looks like a chaotic jumble of complex calculus and super intimidating diagrams. Today, we're going to change that. In this explainer, we're just going to calmly translate all that heavy math back into the simple, elegant, physical realities it actually represents, kind of like learning the fundamental grammar of a brand new language, the language of electricity. To get there, here's our roadmap for this explainer. First, we'll cover electrical core foundations. Next, we'll meet the network elements. Then we'll go over the rules of circuits. And finally, time and transients. All right, part 1, electrical core foundations, push and flow.
Okay, let's dive right in. To understand any language, right, you really need to know its nouns and its verbs. In the world of circuits, the whole shebang boils down to one fundamental relationship: push and flow. It all starts with charge, which is measured in coulombs. Charge is simply a core property of particles, like protons and electrons. But static charge, just sitting there, doesn't really do much for us. We need it to move. And that brings us to current, measured in amperes. Now, you'll often see this super intimidating equation, I equals dq over dt, but let's de-jargonize that for a second. Current is literally just the speedometer of our electrical charge. It simply tells us how much charge is flowing past a specific point over a given amount of time. It's the flow.
But listen, charge doesn't just decide to flow on its own, right? It needs some serious motivation. That is where electrical potential or voltage comes into play. Measured in volts, voltage is basically the amount of work required to move a unit charge from one place to another. So if current is the flow, voltage is that absolutely crucial push making that flow happen. Without the push of voltage, the current, it just sits entirely still. And if you look at the actual source material here, these student notes, you can see these exact concepts jotted down, which really validates what we just talked about. You've got charge, you've got that equation for current showing the rate of flow over time, and electrical potential defined as the work done to move that charge. This isn't just abstract magic, it's a very measurable physical process. So the really cool part is what happens when you combine that push and that flow. You get electrical power, measured in watts. Power, defined mathematically as P equals V times I, is simply the product of voltage and current working together in real time. It's the actual rate at which work is being done by our circuit, like lighting up a bulb or turning a motor. Push times flow equals power.
Moving smoothly on to part 2. Meet the network elements, the characters in the circuit. So now that we have our basic vocabulary, push, flow, and power, we need to introduce the physical components that actually use them. Think of these as the characters populating the sentences of an electrical network. We can basically divide our circuit characters into 2 main factions. Over on the left, we've got active elements. Think of these as the providers. These are your voltage sources and current sources. They're the ones supplying energy to the entire circuit. On the right, we have our passive elements. These guys are the consumers or the storers of the circuit. Resistors, for example, burn off energy as heat, while inductors and capacitors store that energy temporarily, either in magnetic or electric fields. Digging a little deeper into these notes, it's pretty cool how we can classify our characters even further, beyond just active and passive. We have elements that are linear versus nonlinear. A linear element, like a basic resistor, perfectly obeys the proportional rules of Ohm's law. But a nonlinear element, like a diode, that acts a lot more like a one-way valve, totally changing its behavior depending on the direction of the flow. To fully wrap our heads around the physical circuit, we gotta look at its architecture, the map where these characters actually live. A branch is simply a direct path, kind of like a single street where an element sits. And a node is an interconnection of 2 or more branches. It's the intersection where those streets meet up. So our active and passive elements live on branches, and they connect and interact with one another right at the nodes. Which brings us to part 3, the rules of circuits, Ohm and Kirchhoff. All right, so our characters are set on the board. How do they actually interact? This brings us to the grammatical rules of circuits. These are the rules that dictate exactly how push and flow distribute themselves across all those nodes and branches. And the most fundamental rule of all? Ohm's law. It states that the current passing through a conductor is directly proportional to the voltage across it, assuming the temperature stays constant. Written out simply as V equals IR, Ohm's law beautifully connects our push, which is voltage, our flow, which is current, and the physical resistance of our passive elements. Make sense? If you push harder, more flows.
If you increase the resistance, the flow slows down. But as you guys know, circuits are almost never just one simple path. Enter Gustav Kirchhoff. Check out this hand-drawn diagram illustrating Kirchhoff's current law, or KCL. It applies straight to those intersections we talked about, the nodes. KCL is incredibly intuitive. Honestly, it's just a simple rule of conservation. The sum of the currents entering a node must equal the sum of the currents leaving it. Whatever goes into the intersection absolutely must come out. No charge just magically disappears.
Then we have Kirchhoff's voltage law, or KVL. This one applies to closed loops. Think of KVL like a hiking trail on a mountain. You start off at a specific elevation, right? As you hike the loop, you might climb up, which is a voltage gain from a battery. And you might hike down, a voltage drop across a resistor. But step 3 here is the real key. If you hike a complete closed loop and return to your exact starting point, your net change in elevation has to be strictly 0. The algebraic sum of all voltage changes in a closed loop is always 0.
And this right here is exactly why these rules are just so incredibly powerful. Looking at this, we see complex, multi-branched circuit puzzles being solved. Now, I know the math might look a little heavy with the matrices and algebraic equations, but if you look closely at the underlying structure, it reveals something super elegant. All they're doing is applying that hiking trail rule to different loops. By systematically stating the drops around this loop equals 0, these simple grammatical rules allow engineers to easily solve what look like incredibly intimidating networks. Finally, part 4, time and transients, the flip of a switch. So everything we've talked about so far kind of assumes a steady state, a circuit that's just been running smoothly for a while. But real life isn't static. Just think about it for a second. What actually happens the exact millisecond you flip a switch? A circuit doesn't just instantly and magically jump to its steady state. No way. There is a brief period of shock, a period of adjustment. In engineering, we call this the transient response. Let's actually demystify that initial shock reaction. At exactly t equals 0 plus, so that tiny fraction of a second right after a switch is flipped, we can totally strip away the complex calculus to see the simple physical behavior underneath. A capacitor, which is entirely uncharged, initially acts like a perfect short circuit. It enthusiastically just lets all current flow instantly as it begins to fill up. An inductor, on the other hand, resists sudden changes in current. So for that very first millisecond, it acts like an open circuit, stubbornly blocking the flow like a solid brick wall. Because these components are frantically storing or resisting energy, the whole circuit actually takes some time to settle down. We measure this settling time using what's called a time constant, represented by the Greek letter tau. Think of the time constant as the circuit's internal clock. It mathematically determines exactly how fast the circuit adapts to its new reality and eventually reaches a steady, predictable state after that switch is flipped. And this graph beautifully summarizes that entire journey. We see the natural exponential curve of current rising over time in a circuit with a resistor and an inductor. Instead of getting super bogged down in the differential equations, just let the smooth curve do the heavy lifting here. It shows us exactly how the current starts at 0, climbs pretty rapidly at first, and then slowly tapers off as it gracefully reaches its final steady state. It's not an instant jump, it's a natural journey governed by that internal clock. All right, let's bring it all home. We've built this understanding up block by block today. First, voltage pushes and current flows. Second, the active characters in our circuit supply the energy, while the passive characters consume or store it. Third, Kirchhoff's laws act as the ultimate balancing grammar, making sure energy and flow are perfectly conserved at every single node and around every loop. And finally, time constants map the dynamic journey our circuit takes to eventually reach a steady state. When you really strip away all the dense formulas, the language of electricity is simply a beautiful, completely logical balancing act of energy over time. It's this natural ebb and flow governing the devices we literally rely on every single day. I really hope that the next time you flip a switch or plug in your phone charger, you don't just see a black box of intimidating math, but rather an elegant, totally understandable flow of nature. Kind of leaves you wondering, doesn't it? What other incredibly complex systems in our world might just be sharing this exact same simple grammar underneath it all?